Hi students, let us proceed to part 5 of chapter 15, waves. Now here we are going to study about standing waves, or what we call as stationary waves. So if you look at the diagram, you can see a blue line and a red line. In number 1, in the first diagram, the blue line you can see on the left side B, an arrow mark towards the right, and on the right extreme you can see C, an arrow mark towards the left. So these are actually two waves. The blue line represents two waves moving in opposite directions with same amplitude and same frequency. So it is one over the other, and it is constructive interference, a position of constructive interference. The red line shows the resultant of these two waves. Now when the crest comes over crest and the trough comes over trough, we get maximum amplitude, as you see in the first part. And those positions are called antinodes, and they are represented by the letter A. But points of minimum amplitude are represented by N, and they are called nodes. In the second part of that graph, you can see the blue and the two blue waves are split. So you can see B moving towards the right and C moving towards the left. There is a phase difference between the two waves, some phase difference. And the resultant is got, you can see by the red line, and where there is maximum amplitude, you see antinodes, and where there is minimum amplitude, again you can see nodes. The third part, again you can see the wave B going towards the right and the wave C moving towards the left. There is a phase difference of pi, or 180 degree between them. It is an example of reflected waves. Now the third part shows us standing waves. Each closed loop is called a segment. Now in standing waves, the two waves appear to just vibrate in their position. They will not seem like they are moving. So you can see the minimum amplitude positions and the maximum amplitude positions. And the red wave, resultant wave, is just a straight line because they are stationary. Now coming to the mathematical expression for stationary waves. Let us imagine the displacement equation for the first wave, y1 xt equal to a sine kx minus omega t. And the reflected wave, let us imagine its displacement equation is y2 xt equal to a sine kx plus omega t. Now the plus sign comes because there is a phase difference of 180 degree between the first wave and the second wave. So the resultant wave, according to the principle of superposition, will be yxt equal to y1 xt plus y2 xt. And when we make the substitutions, we get the total to be equal to a sine kx minus omega t plus sine kx plus omega t. Now this bracket is according to the form sine A plus sine B. And you know the identity sine A plus B plus sine A minus B will be equal to 2 sine A cos B. And if you make the appropriate substitutions, here A is kx and B we can take as omega t. So we have yxt, or the resultant wave equation, will be 2a sine kx cos omega t. Now 2a sine kx together is the amplitude of the wave, and cos omega t will show the movement of the wave, where omega is the angular frequency of the resultant wave. So let us see some differences in the resultant wave pattern. Here kx and omega t appear separately. That means kx is together with the sine function and omega t is with the cosine function. Then the amplitude of the resultant wave is 2a sine kx. So when kx varies, the sine function varies and the amplitude varies. That is, amplitude varies from point to point. And each element of the string oscillates with the same angular frequency omega, because omega is along cos omega t. Now the string as a whole vibrates in phase with differing amplitudes at different points. So the wave pattern remains stationary. It neither moves to the left nor to the right, and hence it is called standing waves or stationary waves. The points at which amplitude is 0, as you saw, are called nodes, and the points at which amplitude is maximum are called antinodes. You can see a graphic representation here. The broken line and the dotted lines are the two waves moving in opposite direction. So in the first part, topmost part, you can see they are moving in opposite directions. The broken line is moving towards the left side and the dotted line is moving towards the right side, and the blue line represents the resultant wave. Wherever crest comes over crest, maximum, that is maximum amplitude, or where trough comes over trough in a maximum way, that is negative maximum. And wherever the first wave and the second wave comes in opposite directions, that is node positions. So here we have in the second line, we have the waves are moving further apart. Then in the third line we have they are still moving, and in the fourth one you can see again they are coming to the almost to the first position, but they are moving in, they have come to opposite directions. So this graph shows the stationary waves arising from superposition of two harmonic waves which are traveling in opposite directions. Now we can observe a video based on stationary waves. Please listen carefully.
In this short video, I'll be introducing standing waves. Let's begin with the simulation of a string that is fixed at two ends. I'm going to send a single pulsed wave along the string, and we'll watch as it reflects off the opposite end.
So there is a 180-degree phase difference, as you see now.
Now watch what happens if I send a second pulse along the wave sometime after the first. When the two waves meet, they superpose. At some points they will interfere constructively, and at other points they will interfere destructively. This is perhaps best illustrated by sending a progressive wave along our string and watching it reflect off the end. Note that when it does reflect off the end, the two waves, one travelling to the left and one travelling to the right, superpose such that certain points along the wave are stationary, they're not moving up or down. We can call these points nodes. At other points along the wave, we have our maximum displacement. These points we will call antinodes. We should note that if this is one full wavelength, then each adjacent pair of nodes is exactly 1/2 wavelength apart, and the same is true for each pair of adjacent antinodes.
Okay students, I hope you watched that video. Now next we come to modes, normal modes. So as you can see, the most significant feature of stationary waves is that the boundary conditions constrain the possible wavelengths or frequencies of vibration of the system. The system cannot oscillate with any arbitrary frequency as they like, but is characterized by a set of natural frequencies or normal modes of oscillation. So let us determine these normal modes for a stretched string fixed at both ends. So position, before we come to the modes, let us come to nodes. Nodes appear when amplitude is 0. So sin kx equal to 0, kx equal to n pi, where n equal to 0, 1, 2, 3, etc. Now since k equal to 2 pi by lambda, we get x equal to n lambda by 2. By substituting this k value in kx, you get x equal to n lambda by 2, where n equal to 0, 1, 2, 3. Distance between successive nodes equal to lambda by 2. Now look at the position of antinodes. Antinodes appear when amplitude is maximum. Now when can amplitude be maximum? When sin kx equal to 1. So kx will be n plus half into pi. So when n equal to 0, then kx becomes pi by 2 or 90 degrees. When n equal to 1, then kx becomes 3 pi by 2, and when n equal to 2, kx becomes 5 pi by 2, and so on. Substituting k equal to 2 pi by lambda, we get kx equal to 2 pi x by lambda, or 2x by lambda equal to n plus half. So x will be equal to n plus half lambda by 2, where n equal to 0, 1, 2, 3. Now this is the position of antinodes we are seeing. So distance between successive antinodes will be lambda by 2. Distance between a node and an antinode will be lambda by 4. And distance between successive nodes also will be equal to lambda by 2. So let us end this session for the time being. We'll continue in the next session. Thank you, students.